thank you very much for the introduction. I'm very happy to be here in order to present my research activity. Yes, the focus of this presentation is just to enlighten how to produce in some way, some degrees of cognition and automation on software-defined open optical networks. So the first part of this presentation is just related to the contextualization of the key factors that enable such techniques, the use of such techniques. And in the second part, we will see some experimental results that we achieved applying these techniques on different use case scenarios. So let's start a little bit from the context. I grabbed this data from Cisco Visual Networking Index report. So at a first glance, we can see that in the last years, we sense very huge growth in terms of machine-to-machine connections. And on the other hand, if we look at the data exchange among these machine-to-machine connections, we have also an exponential, not linear, growing trend. That means not only that the connections are increasing, but that also the complexity of the system is increasing. So, in recent years, also service providers and operators aim to achieve these three main targets. The first one is the disaggregation of optical networks. The second one is the possibility to have no dependency with respect to the vendor origin of the hardware. And the third one is the possibility to integrate different equipments coming from different vendors within a single system in order to implement interoperability. So there is the need of a standardized language for data structures. And very recently, we had the birth of a lot of consortia and projects that spent a lot of effort in order to pursue this direction. So we have the Open Networking Foundation, OpenConfig, that is driven by Google. It is an operators consortium. Also OpenROADM, driven by AT&T, and finally we have a telecom infra project that we as Politecnico di Torino are part of this consortium. So, given the growing data traffic demand, how we can implement a maximization of the capacity or a full exploitation of the optical infrastructure. So, thanks to the introduction of some degrees of openness in our system at a physical layer, we can for sure introduce and apply these techniques of cognition and automation that for sure will help a lot operators in the deployment of their services. Okay, so which are the fundamental steps that enables the use of cognition or optimization in this context? So the first one is for sure the possibility to expose the data starting from the physical layer, starting from each network element, and the possibility so to abstract, virtualize, softwareize in a perspective of software-defined network, each network element, and to manipulate these objects within a unique orchestrator, which is a network operating system. The collection of all the virtual objects is something that we call usually physical layer digital twin. So it is the virtual representation of the system that we want to apply some operations. Okay, let's start with the introduction of the developed methodology in this research activity The first one, the first step is the characterization of a specified network element. In this procedure is fundamental the use of the telemetry. So we firstly probe the status of the system in a specified working condition. So we measure these metrics of interest, and then we tune the emulator in order to reproduce the same results that we have in field. So we optimize a set of physical layer parameters that we see in green, and the second step, when we have the abstraction of such element, we can instead fix these parameters and play with the working conditions of the amplifier of our network in order to optimize the capacity of our system. So let's start from the first use case. Let's start from a single span of fiber. Okay, this is the application of this methodology on a single Raman amplifier. A Raman amplifier is a set of laser pumps that inject some amount of power into the fiber and produce a certain gain on the propagating spectrum. So it is a quite complex object, but you can see from this picture that tuning properly the physical layer parameters, the emulator is able to completely reflect the behavior that we have in field. So once this is done, we can properly play with the targets that our amplifier, and we can reproduce exactly in field the wanted target. Okay, so now let's pass to the second use case, the open line system. So let's zoom out a little bit the scenario. We have a multiple span system, okay, more than one, and this is the principle. So let's start from the turning on the system. When we turn on the system, the first step is the probing. So there is the configuration of the system on a specific condition in which the telemetry is enabled to measure the status of the system, collecting this information that is passed to the physical layer digital twin. At this point, this organ characterizes the system and produces visualization of the physical layer. So each network element is abstracted, and after that we can play with these objects which are virtual, and we can define the optimal working point configuration of the system in order to maximize some metrics. In our case, the capacity. So this is a little bit what happens when we characterize a single fiber span in a multi-fiber span system. The first step is to use the OTDR in order to understand which is the length of the fiber and the position of all the lumped losses. The second step is instead to turn on the amplifier, the left side amplifier, in order to produce some amount of optical power through the fiber, and we measure, thanks to the optical channel monitors, these two spectra at the input and the output for two different power levels in order to enhance the nonlinearities of the fiber. The last step is the collection of this information for each fiber span and the optimization procedure in order to retrieve which are the optimal physical layer parameters that reproduce the experimental behavior. This is a picture that reproduces the output of the complete characterization of an optical line system. You can see that in this graph we have the effective area of each fiber. Then we have the alpha graph is the loss coefficient function for each fiber span, and we also obtain combining the different information that we retrieve from the field, also we can understand which type of fiber, or at least we can guess which kind of fiber we have in field, even without using any datasheet. So, once we collect all these virtualized objects, the idea is to optimize the system. So we developed two different strategies. The first one is a global strategy, looking at just the quality of transmission at the end of the line, and the second one instead is a local strategy. So we optimize, dividing the overall optimization problem, very small optimization problem, one for each fiber span. So we optimize locally the working point of each amplifier. Let's compare these two methodologies. We have in the first row the local strategy, in the second one the global one, and we see that the local one is firstly faster than the other because we cut the problem into many pieces, and each one of these is very fast in the computation time. So not only this, we also retrieve something that is with a higher average in terms of quality of transmission and even more flat. So it means that even every channel has the same quality of transmission, whatever is the frequency of this channel. So it is a very good point. We have the equalization of the quality of transmission for every channel. Okay, last use case is the application on a complete optical network. A network created in links, a linear topology network of about 1,400 kilometers. And we can see that we have, this is the perspective of the propagating spectrum. This is the A graph is the input spectrum, then we drop two modulated channels after the second switch, and at the end of the network, the second line, we drop the last two channels. Okay, so we validate these, the behavior of this network and also the validity of the applied technique. And we have, in this case, the prediction that are the straight lines, which are always conservative with respect to the markers, which are instead the measurements. So we obtain a very accurate case for the far measurement. Instead, for the closest one, we obtain something that is very pejorative in terms of prediction, but this is, we explain this in the light of the fact that the degradation is not so enhanced, and so also the quality of transmission in this case is very sensitive with respect to the hardware equipment. Okay, so these are the conclusion of my presentation. I showed something related to the characterization, autonomous characterization applied to different use cases, and then also I presented some control procedures which are vendor agnostic with respect to the used equipment, maximizing the quality of transmission in terms of average and flatness. Further improvements can be linked, completing the orchestration, the management on experimental optical network, and then we can also apply in real time some artificial intelligence approach in order to cope with failures in real time. So thank you very much, and I want also to thank all the researchers and partners that support us in this adventure. Thank you.